my video on the big board today. So now I don't know. I might try to get it this year. I normally don't get it, and we're all gonna have masks on, so I feel even less likely to get the flu this year than I have before. So I may not get it. I use the cop out, which is not a good thing to do, but I cop out by saying, leave the flu shots for the people that need it. And if you're young and healthy and you don't get sick from the flu that often, you don't want to take up a flu shot from somebody that actually does need it. That being said, that's not really a valid argument, but it's the argument I use to make myself feel better. But yeah, we've all got masks on, and even if the mask mandate goes away, I'm still going to wear my mask because standing up here and speaking and projecting, I'm probably got the particles getting at least to the second row. Y'all are in the splash zone, so I'll probably wear the mask for a while, and I don't know if I'll get the flu shot. Maybe I should. If any of you wants to make an argument that I should get the flu shot, I will listen. My wife says that I should probably get it. And to be fair, I think I'm probably gonna have to start getting it on a regular basis because we're moving into the age of no. We're moving into the age of childhood, having kids, so I don't want to be getting my kids sick from all y'all germy, diseasey kids. No, it doesn't. You usually get the flu shot around the time that the flu's going around, and so the likelihood is high that you get the flu shot and are pretty quickly exposed to the flu. You can still get the flu after getting the flu shot. More than likely, it will be less severe than it would have been if you hadn't got it. But yeah, no, you don't get the flu from getting the flu shot. That being said, almost every year that I've gotten the flu shot, I did get the flu that year because this is a different scenario because I've never really gotten it at work. But in order to get the flu shot, you have to go to the doctor. And what is the doctor's office filled with? Sick people. And so you're more likely to get exposed there at the doctor's office while you're getting your flu shot than you would be if you just stayed home. So I think that has been my issue with getting the flu every time I got the flu shot. But yeah, I never really thought that I was getting the flu from the flu shot. So I hope everybody at home can hear me on this video. We're going to start with galactic interactions. And I think yesterday I mentioned that the Milky Way is going to collide with the Andromeda Galaxy. And in fact, before I do this real quick, I have a nice video. I wanted to know when that was going to happen, so I just Googled Andromeda Milky Way collision, and a nice Wikipedia page popped up. And we don't have anything to worry about because it's going to happen roughly about 4.5 billion years from now. And in a little bit, the PowerPoint's going to tell us that that's only a 50% chance that we actually hit the Andromeda Galaxy. And so it's not necessarily absolutely going to happen. It's about 50-50. This is a pretty nice video that shows you what's going to happen. They're really in love with their animations here, so they draw this out a lot longer than it should be. But I assume this is the Milky Way Galaxy, and coming in from the left, you have the Andromeda Galaxy, and probably some kind of small companion galaxy, which you could look up, but I don't know the name of. We're going to get close. It actually looks like we're going to miss each other, which is probably contributes to that 50% chance that we don't collide. But our gravities interact. Gravity pulls us together. We go through once, and you see all the stars on the outside, which would be our solar system, interacting because of that pass-through. We come back together again. You get another pass-through, and this time it's more of a direct hit. But remember that these galaxies have an immense amount of empty space there. And so the idea is there's not going to be a whole lot of physical collisions. It's more of an intermingling and then gravity kind of pulling everything around. At this point, we'd probably be having a lot of physical collisions just because you have much more mass in the same kind of area. But we don't really know what this collision is going to look like. And 4.5 billion years from now, we'll probably have our own problems if we're still even around. So it's a pretty interesting video. Know that Wikipedia is really nice. You shouldn't cite it, obviously in your papers, and I'm sure you all know that by now. But some schools and some teachers take that overboard and they're like, you should never go to Wikipedia. Don't trust anything on Wikipedia. Wikipedia is pretty good about keeping the right stuff on there. I've seen stuff changed and they get to it pretty quickly. In order to like really change stuff, you have to have like a pretty high standing with them and have made a lot of legitimate posts. So, you know, I wouldn't go out on that limb and say that Wikipedia is not trustworthy. It pretty much is.
It has its own sites that are not.
Huh?
Use their sites.
Yeah, use their sites. You can tell the sites that aren't super great. Yeah.
Can I listen to all these in my content?
Well, your contact? Come on. Yeah, you can. Okay. Alright. It's about to fall out. Contacts are terrible. They're bad for your eyes. You should just wear regular glasses. I wear contacts. Yeah, I was just talking to that. But it goes for him too. I wore contacts for a long time, and at one point in time, my doctor was like, and I didn't do what y'all do. Some of y'all like leave them in overnight or weeks at a time. I took them out every day and everything, and used clean ones. And at one point in time, my doctor was like, your eyes are literally getting calluses. Hello? Yes, no problem. All right. Dawn, you're in trouble too.
Yes, John.
Yes. So yeah, if you know, if they don't bother you all that much, wear glasses instead of contacts. It's much better. And on a side note, before you let someone blast your eyes with lasers, you better do your research because LASIK surgery is extremely shady. It really is. When you try to do research on it, the only way you can get data is kind of from the LASIK surgeons themselves, which absolutely have an agenda. Almost none of them are associated with hospitals or like actual medical communities. They're just like in a strip mall somewhere. And usually they're like, we'll give you LASIK at like 75% off. And you're like, what is this pricing scheme you have going on here? This doesn't sound like a legitimate doctor's pricing scheme. So I would love to not have to wear glasses and get my eyes laser blasted. But there's a significant portion of people that cannot see better. If the surgery does not go well, it's very difficult to fix and sometimes impossible to fix. And right now with my glasses, I can see. So it will probably be a long time before I risk getting LASIK. That's just me. But do your own research. Don't just walk in the door and be like, yeah, laser blast my eyes. There's risk to it. There's a lot of people who have had it done successfully, but and right now they don't even know how many times you can get it done because it doesn't last forever. It's not going to last your whole life, so you might need to get it done again. The more times you get it done, there's more issues with it. So back to galaxies. When you have these collisions, it's really driven by gravity. So remember that it's not necessarily like a physical collision. It's more of a gravitational mingling. They say a large galaxy may engulf a smaller dwarf satellite galaxy. Their two dwarf satellite galaxies are currently merging with the Milky Way, which I was not aware of. I don't think they're talking about the Andromeda thing because I don't think Andromeda is a dwarf galaxy. Two galaxies of similar size may pass through one another without merging. The interstellar matter will likely interact, the just kind of matter that's floating around in between all the stars and solar systems. It could trigger an intense period of star formation because now that matter that was just kind of floating through will have a gravity source, it will start to condense, and it may form new stars. This is the Andromeda one that they're talking about, from about 2 to 4 giga-años, so billion years. There's a 50% probability that we'll have that collision.
Teachers, pardon the interruption. I understand there's some issues going on with the Wi-Fi with certain people, with Chromebooks trying to get logged on. Ashley Schleich is about to send out an email to you guys with some directions on how you can get them logged back in.
Okay, we'll see. Well, my computer back there has, our desktop, I know I was thinking the same thing, but our desktops have connection. So I assume this is an image of two galaxies merging together. We're going to talk about the Doppler effect for a little bit, and I have talked about the Doppler effect in chemistry, I believe, and I'm going to do a silly little example of this, and I assume the people at home will be able to hear it. So what the Doppler effect is when I'm moving towards you, light waves and sound waves will be compressed because my speed is added to the sound speed. When I'm moving away from you, they will be elongated because my speed moving away from you is subtracted from the speed of sound or light as it's headed towards you. So what you hear, and you can hear this with motorcycles, you can also hear this with cars as they're passing by. As you hear this sound that goes, and it starts high when they're headed towards you, and it goes low when they're headed away from you. So that happens not just in sound, it happens in light. Yeah, it's really funny. I enjoy it. Let's be honest, I enjoy it.
Like the ambulance thing.
Huh?
Like the ambulance?
Yes, yeah. It happens all the time. We use it like the Doppler effect. You hear it almost, well, if you watch the news, you hear it almost every day. The Doppler radar is how we detect weather, and so it uses this effect. We use Doppler to prove or to substantiate the Big Bang Theory. We also use the Doppler effect to find hidden planets out in space. As they orbit around their star, the star gets a wobble because of the gravity. So sometimes it's moving away from us just a little bit, sometimes it's moving towards us a little bit, and we get these little tiny shifts. So that kind of explains the Doppler effect really quickly. A large Doppler shift, so the more the sound changes, the higher the velocity. The less the sound changes, the lower the velocity. So your car has to be moving pretty fast as you're honking the horn to kind of hear that. Now, how this translates to the Big Bang and how we kind of got to this point. Most galaxies that we see exhibit a red Doppler shift. So as we look out into the sky, we can estimate the size of stars, the size of galaxy, what mass they have, in general what elements they're burning, and what color they should be. We're not always perfect at it, and there's been adjustments made to this over the years, but we have a pretty good idea of what color they should be. And when we look out and see them, they're always, or most of the time, not always, because obviously the Andromeda Galaxy is coming towards us, but almost always they are more red than they should be. And this is known as the redshift. And it took us a while to figure this out. But the further galaxies are away from us, the more redshift they have. The closer they are, the less redshift they have, but there's still some redshift. And so the further stuff is moving away very fast. The closer in stuff is still moving away, but at a slower pace. So this was discovered in 1929 by Edwin Hubble. What is his name famously attached to? The telescope. And so Edwin Hubble, because he discovered this, they named the Hubble telescope after him, which is one of the best telescopes we've ever had in space. We're about to put another one out called the James Webb Telescope. It's been delayed for a long time, but it's really close to getting up. It's fully assembled now. And I actually, on a live stream the other day, I heard a really interesting conversation about people wanting to catch the Hubble telescope and bring it back to Earth safely, to kind of put it in a museum so people could actually go and see it and kind of learn from it, which is interesting. But he discovered this in 1929. The law that came from this is called Hubble's law. And note that this is not a theory. This has been tested by enough people all over the world. You can literally go out at night and see this and do the math yourself if you're good enough at math, which I'm not. But it has moved into the realm of scientific law, so it's very, very accepted. The recessional speed of galaxies is proportional to their distance. So the speed at which they're moving away from us is proportional to how close they are to us. The further away they are, the faster they're moving. The closer they are, they're still moving away, but they're moving slowly. And this accounts for the redshifts that we see. So what that means is that led us to the Big Bang Theory. And actually, I'm going to go to the next page because there's a really good explanation here. This is called the raisin bread example, which seems silly, but watch and you'll see. So this is raisin bread dough before it rises. And we're all familiar with dough rising. You have yeast in here. The yeast gets activated. It produces a chemical reaction which makes oxygen. The little oxygen bubbles start to fill up as they propagate their dough, and your dough literally rises. Now, from this first picture to the second picture, imagine the raisins as galaxies. So you start to measure your distance to all the galaxies around you. And as the raisin bread rises, it doesn't really matter which galaxy you pick. If you went in and measured these, literally every single other galaxy is moving away from that raisin, or that galaxy. And so this 2 centimeters turns into 4, this 6 centimeters turns into 12. The further away you are, the faster you're traveling. The closer up you are, the slower you're traveling. And so this is kind of a good example of the expansion of space that goes into the Big Bang Theory. So I'm going to go back one slide, and we're going to go through the details of the Big Bang. So it counts for those galaxies moving away from us. It says the universe was confined to a ball that was supermassive, dense, and hot. I've always taken issue with what they call this. I definitely don't like the ball in quotation marks. The term they use is singularity, and I've always wondered, why don't they call it a black hole? That's literally what I think it is. If it is not a black hole, it's not very different. And the singularity thing kind of makes it more difficult for everyday people to understand. And so I think if you called it a black hole, it would be much, much more relatable to normal people. So I'm going to kind of refer to it as a black hole. But the universe was once combined in this black hole. The Big Bang marks the inception of the universe. It occurred about 15 billion years ago. I think the current number is like 4.7, 4.6, depending on who you ask. All matter in space was created. This is a little bit iffy because the ball was essentially all matter in the universe. You could say that it's created because of Einstein's equation, E equals mc squared, which allows for matter and energy to be transferred. So you can take matter and turn it into energy. You can take energy and turn it into matter. So that whole idea, matter cannot be created or destroyed, kind of goes out the window with the E equals mc squared equation. So all matter in space was created. The fact that space was created is very well understood. When you have this ball, there is no space. Like if you had a time travel machine, which again isn't going to happen, but if you went back in time in your spaceship time travel machine, you wouldn't be able to just fly around the singularity and look at it. Essentially, at this point, there is no space, there is no time, and all matter that exists in the universe today was inside of that singularity or inside of that black hole. What we see today is the matter is moving outward, like everything is expanding. We see it in the galaxies. We have a lot of evidence to support this. Now, here we get to the depressing part. And I imagine that most astrophysicists today are just really sour people that are super depressed. Because we only have two possibilities for the eventual end of the solar system. There is no good news in this. One, the universe will last forever, which is actually not a real thing. The universe will, but the things in it will not. This one is basically forever outward expansion. And what that leads to is the heat death of the universe, meaning I poured this tea the beginning of first period. This delicious jasmine tea. And right now it's pretty warm. It's not hot. I could probably down the whole thing real quickly, but I'm not because I want to enjoy it. But, give it an hour and it's just going to be room temperature. It'll be literally the same temperature as everything else in this room. Because one thing that heat does, whether you're in space or on this planet, it doesn't like to be contained. Heat spreads out. It will spread out as far as it can. It will dissipate itself. And so if the universe continues to expand, essentially, over a given period of time, all the stars will burn out, all the matter will spread out as far as possible, and the heat will just go down to a level where life cannot be sustained. Everything will be cold. The stars will be so far apart. If you were on a planet, Earth won't be around by then, but if you were on a planet, the sky would just be black. You wouldn't be able to see any stars. They would be so far away from you, the light would never reach you. And essentially, the universe would just go cold, and it would be impossible for anything to live there. You wouldn't even have material to create things. There just wouldn't be any storage of heat. Now, obviously, this is over an extremely long timeline, well beyond the billions of years into hundreds of billions or trillions of years. And so it's a crazy, crazy distance. We don't have anything to worry about now. But if you're a future-looking person, it's a bleak outcome. The second outcome is the exact opposite. Your outward expansion will stop, and gravitational contraction will follow. So essentially, the masses at the center of the universe, which are close to where the original Big Bang happened, will eventually grab everything in their gravity. Outward expansion will stop, and at some point in time, inward collapse will happen. This is called the Big Crunch. And what that would lead to is essentially a recreation of this black hole or singularity or ball, as they call it, where everything gets sucked back into the middle, and essentially we all get crushed by gravity, and everything gets wiped out again. An interesting thing, Stephen Hawking kind of proposed this about black holes, and it definitely deals with the Big Bang as well. If there was anything before the Big Bang, we will never be able to know about it. Black holes essentially are information erasers, where we can look out in the galaxy right now, and even though we can't go there, we can see the light from things, and we can determine information about them. That is information that's literally headed towards us. We can learn all sorts of things. And so matter kind of stores information in a way, especially when you get into the physics area. Black holes erase that. They make it go away. And so we'll never know if there was anything before the Big Bang. I kind of believe there could be, especially if the Big Crunch happens. You could just have like this cyclical thing where it all goes back into the singularity, and at some point the singularity blows up again, and everything starts over. But that's not a widely held belief in the scientific theory. So the fate of the universe depends on the density of the universe. If the density is more than the critical density, we will contract and we will get the Big Crunch. Current estimates say that the density is less than the critical density, and we will just continue to expand out forever and eventually suffer the heat death of the universe. Now, what could change that? What property does the universe possess that will determine its final state? Dark matter. We know that dark matter exists. We're not good at detecting it. We don't fully understand it. We don't know how much of it is that there is. If there's a whole bunch and we haven't found it yet, that could give us enough gravity to kind of stop that outward expansion and eventually pull everything back in. That being said, that still remains to be seen. And I guess technically, if you want to be fair about it, there could be a third like Goldilocks scenario where there's enough gravity to stop the outward expansion, but once we get out there, it doesn't ever really pull us back in. But I don't know that that's a thing. Maybe it's like the whole universe is spinning and we're just like in an orbit around it. I don't know. You'd have to be really good at math to work out the math for that. So that's where we're at today. What time do we have?
10 minutes.
10 minutes, cool. I'm turning the lights on. I want to do one thing real quick because tomorrow we're going to watch a really, really good TED Talk. And he's going to talk about time dilation, and he's going to talk about antimatter and matter and antimatter rockets. And one thing I want to talk to you about is a concept that he really segues into very quickly. And so instead of stopping the video and having to explain it, I want to talk to you about it now. So tomorrow you're like, okay, the 1G rocket. So what he's going to mention and segue into quickly is a 1G rocket. And what he means by that is a rocket, and he's going to talk about antimatter, and they're making like antimatter rocket engines essentially. And the idea is if you had an engine efficient enough, and an antimatter engine technically possibly could be, you could just leave it on the entire time. You never have to turn it off, which is not how we travel space right now. When we leave Earth, we turn the rocket engines on for like 15 minutes, and they get up into orbit, and then we turn them off. And in orbit, like the people that are on the International Space Station, they're in 0G. They call it microgravity, but 0G. So they're just floating around, which is not good for your health. We were made to be here on this planet in 1G, and anything outside of that is not good for us for prolonged periods. When we go to the moon, they turn the engines on at the proper point, usually on the other side of the Earth. They slingshot around, but they only leave them on for, maybe 15, 30 minutes. Depends on the size of the rocket and the size of your engines. But if you left them on the whole time, A, you run out of fuel way too quickly. B, you'd be going too fast to stop at the moon when you actually got there. And so we definitely do not have a rocket that we leave the engines on the entire time. I'm going to make an Expanse reference. If you like science fiction books, The Expanse is awesome. If you don't like to read, there's a TV show on Amazon about The Expanse, which is also awesome. It's got some adult stuff, but it's not anywhere near the level of like Game of Thrones or anything. So it's a really good show. But in the Expanse, what they do, they have 1G capable rockets. There was an efficiency breakthrough in rocket technology, which allowed us to colonize and live on these moons and planets further out in the solar system. But one thing they write about really well is how that travel works. So you leave Earth, for example, let's say you're going to Jupiter or a moon of Jupiter. You leave Earth, you leave the rocket on the entire time. And essentially, you experience 1G. Let me erase the landing legs. So while your rocket is burning and the propellant is going out the back of the rocket, it's constantly accelerating forward at 9.88 meters per second squared, which is the acceleration of gravity. So you in the rocket, your feet will be oriented that way, and you will be constantly pressed against the floor, and you will feel like you're just standing on Earth. Obviously, you'll probably feel a little bit different, and especially if the rocket has to turn and make course corrections. But you essentially feel this gravity. Everything's nice and comfortable. You can do work easily. You don't have to worry about tools floating away or you being oriented the wrong direction. It's just nice and easy. The problem is, if you do that the entire time, you'll either smash into Jupiter or just keep going past it once you get there. And so they talk about the maneuver called the flip and burn, which is halfway there, you're already going pretty fast because you've left your engine on the entire time you've been accelerating. So in order to stop when you get to Jupiter, you have to stop halfway, turn your rocket ship around, and actually burn your engines the other way. So the second half of your trip, you're decelerating at 1G, which puts you right at Jupiter at a speed that's either close enough for you to land on the moon or to enter into orbit and get where you need to go. And so this idea of slowing down is very important in space travel. Now, what he's going to talk about is if we get this rocket and we're not going to some place here in our solar system, we're just exploring. We're getting out there. We want to go to other galaxies. We want to go to the edge of the universe, like explorers on Earth went to the edge of the known world. We want to find out new things. We just leave the engine on the entire time. Now, very quickly at this acceleration, you're going to get close to the speed of light. And so I think, I don't remember the time frame. He'll go over it in the video. But he talks about once you get to the point where you're like 90% of the speed of light, which is absolutely crazy. Right now, all our current rockets don't even get to like 1-2% of the speed of light. That's very, very fast. So 90% of the speed of light would be insane. But with 1G rocket, you could easily get there if you left the engine on the entire time. You could even get to 0.9999999% of the speed of light. But at 90%, I think, you start to experience time dilation. And that's what they kind of covered in Interstellar. So he goes near the black hole, he's on the planet for like a couple hours, and by the time he gets back to Earth, his daughter is like in her middle ages. She's aged like 20-30 years, where he hasn't aged a day. That is time dilation. We get time dilation when you're going either very, very fast, close to the speed of light, or you're near something like a black hole or a huge star that actually bends the fabric of space-time. And it's all way out there, but apparently it's very accepted in the scientific community, especially for the people who are smart enough to do the math, which I'm not. But I guess the last thing I want to add is if you were ever able to go at the speed of light, which we couldn't. Essentially, here's the weird stuff. If you were going the speed of light, you are light. You're not matter anymore. You only exist as essentially like a light being. You're super stretched out, and you're just light. But at that point, if you were able to do that as a sentient being, time would stop. Like, I don't know what you would experience, if you would be conscious or if it would just be instantaneous, but no time would pass during the portion of your trip that you were traveling at light speed. Obviously, time would pass for everything else around you, but time would just stop. Now, anything less than the speed of light, even if you were 99.9999, very far out, percent, you would have some time pass, and you would not be like in this phase of light, I guess. And all this sounds very weird, but it's very interesting. You don't have to be a scientist to kind of be in it and watch YouTube videos on it, or read little articles or books. But that's kind of what he's going to get at tomorrow. He's not going to get into like you becoming light thing, but he's going to get into if you had a 1G rocket and you were able to leave it on for years or decades at a time, you could get at like 99.999% of the speed of light, and the places you could go would be very, very ridiculous. Now, by the time you got there, the world you left behind would be gone. The time difference between you and the Earth would be extreme. In some cases, literally the sun would have expanded into a red giant and the Earth would be gone. And so if we ever really do travel out to the stars, we have to take everything with us. That knowledge is never going to come back to the Earth. Like, it's not going to be something that the people here benefit from. It's a one-way ticket. Almost like if you think about travelers in early Earth, you get on that ship, there's no mail system, there's likely not a return trip. You're going there and you're using your ship when you get there to build your house, and you're taking everything with you. Like, whatever you learn probably isn't going back for those very first boats. Now, obviously, in the time of Columbus, there were return trips and there was information that got back. But like early Viking settlers, early nomads that walked across the land bridge, there was no, we're going to tell people about where we went. It's we're going there and we're staying there, and everybody else essentially is dead to us because we'll never see them again. And so it's a really weird thing that he kind of talks about, but it's only like a 15-minute TED Talk, and we're going to watch that tomorrow. So I need to remember to stop my video. Thank you for tuning in, our home students. And remember to like and subscribe. Where are we at here? Nope. No.